Bismillahir Rahmanir Rahim. First of all, I would like to thank the professors who organized this conference, the first national online conference in material physics. My participation is titled by Theoretical Prediction of the Structural, Electronic, and Thermodynamic Properties of the Half-Hessler Compound, written by Bachiri Zeyneb. The participation contained these outline: introduction, computational method, result and discussion, and finally conclusion. Introduction. Half-Hessler are known as the best materials for different applications such as optoelectronic, electrical, thermoelectric, and piezoelectric application, etc. Half-Hessler possess high spin polarization, exhibit half-metallic property. After we move to the computational method. In this study, structural and electronic properties of cubic half-Hessler compound LEGASE have been reported using density functional theory, DFT, as implemented in ABinit code package. For exchange correlation potential, we have used GGA PBU. The last part of our study deals with the investigation of the thermodynamic properties of the LEGASE. We used the quasi-harmonic Debye model implemented in the Gibbs-2 program. For the result, we have did the convergence test to determine key point and cutoff energy, the calculation of structural parameters such as the lattice parameters and bulk module beta of our compound LEGSE are presented and compared with the experimental and calculation value in Table 1. And we can see that our calculation of lattice parameter is in good agreement. Then we have electronic properties. Figure number 1 shows the electronics band structure of LEGASE along the principal symmetry direction of the Brillouin zone. From this figure, we notice the maximum value of the valence band for the LEGASE is at point gamma, and the maximum value of the conduction band is at point X. That is to say that the compound LEGASE have indirect gap, each indirect semiconductor gamma X. In Table 2, we summarize our results of band gap energy along the principal directions gamma gamma, gamma X, gamma L of the compound LEGASE, compared with other data available in literature, and it shows that the calculated band gap of 0.215 electron volt for LEGASE is in accordance with the previous theoretical results. For the thermodynamic properties, we study the effect of temperature on some properties, and these were the results. We see in Figure 2 that the unit cell volume increases with the increase in temperature, and it can be seen from Figure 3 that there is a decrease in bulk module with the increase in temperature. From the Figure 4, we can see the thermal expansion coefficient alpha increase rapidly at low temperature, while it increases slowly at high temperature. And Figure 5, we see that the entropy S increases with the increase in the temperature. The Figure 6 presents the temperature dependence of the calculated heat capacity at constant volume, CV. In the low temperature, it increases rapidly with T-cube, and in high temperature, it slowly increases and converges to the Dulong-Petit limit. In Figure 7, we see that the heat capacity at constant pressure, Cp, have the same variation of Cv till the temperature 600 Kelvin, after it increases rapidly. Finally, we can conclude this work in: we have investigated structural and electronic properties of the LEGASE half-Hessler by using the first principal calculation based on the plane wave pseudopotential method within the GGA approximation, specifically the lattice constant, bulk module, band gap, and their related quantity. We calculated the optimized lattice constant for LEGASE are in reasonable agreement with the theoretical finding available. We found that the LEGASE are indirect semiconductor gamma X. The various thermodynamical quantity in the constant heat capacity, thermal expansion coefficient, and entropy are examined and discussed were also calculated under temperature. Thank you for your attention.